Oh,
second Boston Kafka Meetup. We're really excited to have as many people attend. First up is going to be Bill Bejeck from Confluent, and he's going to do a little intro. So thank you.
Okay. Thank you. Everybody hear me okay? Okay, great. So I'm here to present Kick Your Database to the Curb. So off the top, I'm going to apologize for the clickbait title because obviously I'm not going to say that, hey, you can get rid of a relational database and this is going to solve all your problems. But interactive queries are an effective tool for building powerful microservices with Kafka streams. So I'll do a brief introduction on myself. I've worked at Confluent for 2 years now, that whole time on the Kafka Streams team. And I also wrote a book called Kafka Streams in Action. And I'd like to take a moment to give a special thanks to Victor, who helped me a little bit with the slides. Engineer first, presenter second. So, all right, so let's cover the agenda of what we're going to talk about tonight. Just a brief discussion of what is state and why would we need state in a streaming application. And then how many people here have heard of Kafka Streams? Okay. Is anybody using it right now in production or? Okay, a couple of hands. Okay. So we're going to do a quick overview of Kafka Streams, and I'm going to do it in a little bit of a unique way. We're going to talk about life before Kafka Streams, and then show you how you would build a streaming application with Kafka Streams. Then we're going to describe interactive queries, and then we're going to do a live demo. So first, let's start with just a simple stateful application. I'm sorry, no, what is state? Why would we need state in a streaming application? Okay, cool. So the answer to that would be, it's information your application needs to remember beyond the scope of current record that you're working with. So, in a streaming application, each event could be considered in isolation, but a lot of times you need details from that event to complete the full picture. So with that in mind, let's just think of a simple streaming application we would build just using regular Kafka consumers and producers. So it's just you just write a regular Java class, you have your main method, and then here we have send interval, which will come into play in a minute. And this is our local state. It's just a hash map, group by count. And then we're going to instantiate a consumer and a producer and subscribe to some topics. Now, to do that, after that, for it to be of any use, we're going to need to start consuming those records. And you can see we're going to consume the records. And basically, we're going to assume that the records are coming in with key data. Kafka obviously works with key value pairs, but in this case, we're just going to assume it's coming in with key data. And you access your local state and you see if it contains it. If not, you're going to initiate the value. And then no matter what happens, you're going to increment your count by 1 and then put it back in your hash map or your local state store. Now this data by itself, it's not going to do you much good, so you have to publish this to the outside world. So you're going to, another point is so you want to iterate over your state to send that out. But for every update, you don't necessarily want to, if you have like a lot of updates, you don't want to just keep sending, incremented by 5, 6, 7, 8, 9, and so on. So you're going to, when your counter, this is kind of a crude method, but when your counter equals your send interval, then you're going to iterate over your state. And then for each record, just create a producer record, and then you're going to send it, and then you're going to commit your offsets. So it's a really simple application, but you're doing a lot of things by hand, a lot of manual things. You're creating your producers, your consumers, you're handling, creating the record, and you're also handling committing the offsets. So let's take a look at how we would do this in Kafka Streams. So you would create an instance of a stream builder and call stream builder.stream, and then you give it your list of topics. Now this under the covers is going to set up the same subscription for your embedded consumers, but you don't see that detail. Then your next step is, this is where you want to do the grouping and your count. So we're just going to say group by key. And again, we're assuming this is coming in with key data. If it was not keyed, there's an overloaded method where you could give it a function and tell it how to extract the key. But that would require a repartition, so I didn't want to get into that tonight. But so we're just going to assume that, as I said before, the data's keyed. Then we're going to count. Now, count is a stateful operation, and a stream is, to give you a little more context, a stream is a K-stream object, which is an event stream. So every record is considered independent, even if they have the same key. Each one is considered independent. But count returns a K table, which is an update stream. So in that case, each record with the same key does matter, and it's considered an update to a previous record with the same key. That's an important distinction. But we're not going to really operate on a K table in this application. So we're just going to convert it back to a stream so we can send it out. And then we write to our output topic. And then produced with is just a way that we can provide serializers for the producer to write that data out. So now, I'd mentioned stateful operations in Kafka Streams. Anything that's, when you do joins, windowing operations, aggregation or reduce, that's a stateful operation. And Kafka Streams is going to automatically create a state store. By default, they're persistent stores, which RocksDB is the default implementation that we're using for persistent stores. In our current release that's coming out in 2.3, we actually have now an in-memory version of Windows stores and session stores. Before, you only had persistent versions of those. So now you have it. So that's, anytime you use any of these operations, you're going to get a state store, stateful operation. So now that we've talked about that, let's talk about the typical way of how we would make data available to the outside world. So you've got your Kafka Streams application, and it's going to interact with Kafka. It's going to read from the source topics, do some transformations, and write it back out. But you need another application that's going to read that external result topic and do something with it. And typically, it's going to have to store it in some sort of data store, a database. So you're going to read that. And then again, to make it useful, you have to expose it to the outside world. So you might have a REST endpoint that you expose. And then clients are going to hit that REST endpoint to retrieve the data. So what we would do in Kafka Streams, how we would make it available. Or actually you end up writing extra code. And this is in your external application. You're going to pull again on the final output topic, and then write this out to your external service, write this out to the database via an external service. So in Kafka Streams, how would we enable enable the ability to view state? First thing we would do is we go back to our original application. Now we're saying count materialized as. So I said before, a stateful operation always creates a state store, and that's true, but it's not automatically available for query. So we'll give it a name. If you just do count without passing a materialize, it'll get an internal name, but there's no way to access it. It's just used internally to keep the state. But now we're saying we want to be able to query this count as count store. That's the first piece. Second piece is your configuration. You're going to give it the application server config, and that's a host and a port. And this is going to be important because this exposes that instance to being able to serve up queries from the state store, but it's also going to be used by the internal RPC mechanism to do queries between instances. And we'll talk about this in a minute, but not every instance of Kafka Streams, the state stores, is going to have all the keys available. So now our architecture looks something like this. You have your application, you have your embedded RPC, but now clients can, that endpoint that you expose can just hit that directly, and they can see the results as they're coming through your application. So the importance of the application config is that the Streams instance is not going to contain all the keys. And Streams, if it doesn't have but you don't have to query all the other instances. Let's just say you had 5 Kafka Streams applications you spun up. You would only have to query one. And if it doesn't have it, it's going to use a mechanism to query to figure out which of the instances does have it and return that result to you. So essentially, a single Streams instance is a proxy for all the Streams application instances you have running. But this would be for Streams instances with the same application ID. That's the key point. So mention the host name and why that's important and how does that get propagated out to the other clients. So you're going to spin up 2 instances here, A and B, and you give them these host names are in your config. As each instance comes online, it's going to connect to the consumer group coordinator. And then when it connects, it sends out metadata. The consumer group coordinator, when it detects a new member, it's going to trigger a rebalance and then give partition assignments and send metadata back to each client in the group. So in this case, we have 2 instances that are sending up their host name information. They're going to join the group, a rebalance happens, metadata comes back, and now each instance has the host data of all the other applications within your Kafka Streams. I don't want to say cluster, but like you've stood up separate 2 or 3 applications, so they all have it. And the important part of this is that during a rebalance, when partitions are assigned, Kafka Streams starts assigning tasks to all the instances. And part of that, it builds up metadata based off of host name and stores. So basically, each instance is going to have a mapping by host name of which host has which store and which partitions they're responsible for handling. So I mentioned tasks before and why a Streams instance might not have all the records on one instance. Kafka uses partitions for parallelism. In Kafka Streams, an input partition gets converted to a task, and a task is it's the lowest unit of work within a Kafka Streams application. So in this case, we've got a simple topic with 4 partitions, and we've got 2 apps. So each one of these applications would be assigned 2 tasks representing 2 input partitions. Further, we assign state stores per task. So each instance would have 2 state stores. So in total, you've got 4 input partitions, which equate to 4 tasks. So you're going to have 4 state stores. So all the data is not going to end up on the same instance or the same store. So how this looks in practice, you get data coming and assume, let's just say that this was a topic with 2 in partitions. Something with the key of energy is going to go to partition 0. That's going to go in application A. But finance is written to partition 1. That's going to application B. So, but you only want to expose host A as your endpoint for serving up queries. So you're going to approach it. You're going to send the request in. It's going to get that. It's going to look up. It's not going to have it. It knows that B has it, and it's going to issue that query on your behalf and return that. So now at this point, let's look at going back to the technology that we would use. In our Kafka Streams application, we're going to embed this with Kafka Streams. Gives you the metadata and the plumbing, so to speak, for doing RPC, but there's not an RPC framework provided. So in this case, I've chosen to use Spark Java Web Server. It's just a small server that makes it easy to do RESTful services, but you could use a variety of things. And the client, we're just going to use a simple single-page application with JavaScript just to drive the updates. And now let me just going to do okay, where is browser is not. Where is the, okay. This is part of the demo, but it's not what I wanted to show you. I don't know why yeah. Okay, we'll deal with it in a second. So we're publishing the data, and then we can see the records are coming in here, and they're running over. All right, we'll have to just move on. Okay. So we'll try and get back to that. So we've got the Spark web server running internally, and it's going to service these requests. So the code that drives this, how we embed this is in our Kafka Streams application. We've got our create an instance of Kafka Streams. But we're also going to create, this is a custom class, interactive query server, and it's just a wrapper around the Spark Java web server. And they have a dependency on each other. Interactive query server needs an instance of Kafka Streams. But Kafka Streams, actually, we want to embed the query server in Kafka Streams, and there's a reason for that. Interactive queries are not available during a rebalance. So when a rebalance occurs, if you were to issue request interactive queries, it would result in an error, and you couldn't access it. So it would be nice to be able to detect when we've moved into a rebalance state, or if it's not in a running state, so that we could not even issue the query, not even request the pushbacks to Kafka Streams of request for the data. So how you accomplish that is with the Kafka Streams state lister. And this notifies you of all the state, this gives you a callback to all the states that a streaming application could go through as it transitions. So in this case, when we've gone from the state listener, you get the new state and the old state. So in this case, when we've gone from rebalancing to running, we're saying, okay, we can serve queries, go ahead. But now the opposite case is if it transitions out of a running state, we don't want to support any queries. So now we've seen, this is the part that would go into Kafka Streams application itself. Now we're going to dive into the interactive query server object to see what we would do there. Spark Web Server provides a lot of functionality out of the box. It makes it easy to do RESTful services. And one of them is this get method, and it's just done with a static import. And you give it a path and a response handler, which is just a functional interface. So we can pass in a Lambda here. And this ready is the variable we set before in Kafka Streams from the state listener. So basically, if we can serve up, or if we get a request in, if it's ready, if it's in a running state, we'll go ahead and fetch the records from the session store. Otherwise, we'll just return a message that the stores aren't currently available. So now let's take a look at what's going on with our fetch from session store. So we're going to extract the parameters. And the first thing we need to do is to look up who has the data that we're looking for by the store and the key. Who has this? So we're going to go into get host info. And there, this is where we need the Kafka Streams reference, because Kafka Streams has several methods for operating on the metadata. And we're going to say get metadata. We're saying metadata for key. And this is going to return us a Streams metadata object. But we're really only interested in the host info. And this is going to tell us, for what you're looking for, where does this exist? Do I have it, or does someone else have it? So now that we've returned that, first thing we do is check, does the host name match my host name? If it is, then we would go ahead and, fetch the result. But in this case, this is like the proxy query part. It doesn't, so we're going to issue the exact same query to the host that we just retrieved from the metadata. So now we're going to issue that, and this is going to build up the same parameters. Session is the root of the path, and then the parameters fill out the rest, and then that would be returned. So now the next step is we've found the correct store that we're going to extract the information from. So the next step is to actually read the data out. And now we use Kafka Stream store. You give it the name of the store and the type. So this is a queryable store type session store, and that gives us a read-only session store. And this is a really important point, that with a read-only session store, as the name implies, you can't do any kind of mutation to the data or corrupt it in any way. It's a read-only view, and it's a point-in-time view. There's no contention or locking. You get an iterator, and so the values you're retrieving here could be updated right after you rendered them. But once we have our session store, we just do an iterator, and I'm not going to, it's just a standard iterator pattern where you would loop over and extract the results. So here we've got our results, and we're going to use JSON to return to the clients, and Google JSON to render it to convert it to JavaScript and send it across the wire. So that covers what we're doing. So we've talked about how we're going to do it in Kafka Streams, how we embed the web server in Kafka Streams, and then what we're going to do in our web server or the RPC mechanism. But now let's move to the client. And it's just going to be a simple page application. And it's just going to be stubbed out like this. We just have elements, nothing in it. And we'll have multiple divs. And what we're going to do is, as results come in, we're either going to update the value or just append a value to the row. And we just do this with just regular JavaScript. I believe I used jQuery, but apparently that's really old now. So I think I'm like 5 frameworks behind or something like that. But anyway, so this is the function we're going to run. And that's this is the name of our session store right here. And then customers is just a list of customer IDs I've done to drive the application. And then these are the references to the session table and session header for updating. And then to drive it, we're just going to use the native set interval method and run the load IQ tables every 7 seconds. And let me see if I can try one more time.
Or maybe try stop sharing and then. Like here, click on stop sharing.
Okay.
Once that
There we go.
worked better.
Yeah.
And maybe just go and share it again. Right, and then.
Hit present now again.
Oh, and I have to switch. This one, I think. So now.
Oh, I do. Present now.
Yeah, present now. We can try the HDMI.
Okay. It was so funny. One of my colleagues said,
That's like super small.
yeah.
I think sort of zoom, if you click on those 3 dots.
Hey, let's do this.
Oh, there you go.
Okay. So now it's, and yes, I'm using the equivalent of a blink tag. Sorry to say that, but so you can see as it comes in, and this is actually running on, I'll show the screen in a second, the terminal screen. But this is fake data that's being pumped through locally. But this is hitting the session store, and it's just rendering as it goes. And okay, we'll give up on that. Okay. What I was trying to show is I have the Streams application, when it doesn't find it, it prints out to the console that it didn't have that. And it was like, okay, this is on another instance. It was just another way to demonstrate them, that point. So in summary, interactive queries is it's a powerful abstraction that helps you with stream processing. It's not the right answer for all cases. A lot of times another type of data store might be useful or might be appropriate, but with interactive queries, it gives you more choices. The source code for most of the source code for this came from the book, and this is the interactive query server, but all the pieces for that are available on that GitHub repo. And then Confluent, we have the Kafka Music example. We have the Kafka Music example, and then the Streams movie demo, which also can be used for setting up interactive, demonstrating interactive queries. And for an RPC framework, I forgot to include it here, but Lightbend contributed. They've got an RPC framework that's written in Scala. I haven't used it personally, so I can't attest to it, but there is one out there, if you didn't, I think that allows you to just kind of like plug it in. And then Spring Boot, I believe, also has a lot of support for active queries. And that's what I had today. So stay in touch with us. We've got our Slack community, our blog. I'm on Twitter at Bejeck. And of course, everyone has to say we're hiring. And there's one other thing I wanted to talk to. Confluent has started a Confluent Community Catalyst program. Well, what this is Confluent's own MVP program. So for people that are, this could be yourself or someone you know, for people that are really active in the community and that do a lot to help with Apache Kafka or even Confluent. So you can nominate those people and they can get recognition, or you can nominate yourself. The nominations are anonymous, so no one will know if you submitted it for yourself. And then finally, we've got the Kafka Summit coming in end of September of this year. And with that code, 25% off. That's it. And that's.
Cool, thank you.
Yeah.
Sure.
Okay.
That's a question.
Yeah.
How much overhead is there against others?
That's a good question. I don't have a good answer for that. You mean overhead? You mean in terms of?
Where you were saying it knows about
Yeah.
things that jump across to the other one. Does it slow down the mainstream?
I don't. It depends on the box, but I don't think so, because that's going to happen on a separate. Because that's happening at the query, like that happens in that embedded web server. So that happens at that level. So I don't think it would have too much impact, but it depends on, on the box you're running, how many cores you have available.
So now you've got one that has to stop and say, okay, I need to send a query over to this one. Everything else freezes.
No, it's not going to stop. So because when you hit that endpoint goes to the query server that we've embedded. So Kafka Streams itself has no idea that it's being queried. It's just processing along. It's merry away. And the RPC framework that you put in, that's the one that gets the call and handles the fetching. So there might be, because it's going to hit the state store, and it's going to return an iterator. So if you had, a lot of threads coming in to hit that, it's returning iterators. So that would cause something. But I think that's where you would run into it. But just serving up the queries itself, it wouldn't necessarily, because like I said, Streams isn't going to stop processing to serve those queries.
Related, I missed. Why would you have?
So you have, to properly answer this question, you've got partitions. And in Streams, a partition gets converted to a task. When you have multiple instances, Streams does its best effort to evenly distribute those tasks across all your instances. So in the case here, we're just keeping the example simple. If you have 4 input partitions, that's going to be 4 tasks. And if you have 2 Streams instances, that means each instance is going to have 2 tasks. And those tasks represent 1 partition. So one instance is going to have partition 0 and 1, and the other instance is going to have partition 0 and partitions 2 and 3. And then we assign state stores per task. So you would end up with 4 stores on 2 machines. So depending on where the key was, each instance isn't going to get all the keys, and it's certainly not going to have them in 1 store. So that's where I have to look up.
Any other questions?
Yes, I was wondering if you could talk about the different store options, the trade-offs. But then you mentioned there's an in-memory store that's available now, or there are 4 store options available. Why would you choose one or the other?
Well, one thing I forgot to mention when I was talking is all stores by default. So the default mode is a persistent store, and that the underlying implementation is RocksDB. Now, Streams gives you the ability to provide your own custom store. So that could be something that's not even local, because all the state in Streams is local, but you might have a need for, say, reaching out to Redis or something like that. So you could provide a custom store that's a wrapper around that. And then you have a in-memory store, which you can specify. Default is persistent, so you have to, when you have your materialized, when you do group by key, you pass in a materialized object. That materialized object is where you would give it a store builder, and then you could specify in-memory store. But all stores, whether they're persistent or in memory, are backed by default by a changelog topic. So even if you have an in-memory store, if you shut down the application or it crashes, when it comes back up, it's going to be restored to the last committed offset of what was in your changelog topic. So, in-memory is going to be faster. Joins right now, it has to be, you don't have an option of doing, I guess if you wrote code yourself, you could, but joins are always right now, or persistent stores. And then now we have in-memory session stores and in-memory windowed stores. I guess performance would be the biggest key there.
Query performance or
Just performance of streams in general. And do you need all the data? Because the in-memory stores are going to be limited to a certain point how much they can store. Whereas with rocks, you can it'll keep a fair keep most of the history. Mm-hmm.
All right, we've got tribal scale here, but first I just want to introduce Vinay Narayana. He's the head of the distributed systems team at Wayfair, and wanted to say a few words.
Hi, everybody. First of all, I want to thank you all for
Thank you.
coming here for the meetup. This is our second meetup. Good to see a good turnout. We will be continuing to do these meetups going forward, hopefully once a quarter. I also wanted to take this opportunity because we have a bunch of Kafka people here interested in Kafka. My team is hiring, just like Bill said.
Vinay and I got to fight who gets to interview people. So.
They're looking for a senior developer from team. If anybody's interested, you reach out. The last time we had a couple of people reach out and interview with us, but then we still are looking for more people. If you are interested, reach out.
Okay.
All right, and then if the people from tribal scale can come up here.
Okay.
I'll get you guys set up. If anyone wants to use the restroom while we're getting set up, it's through the back doors in the kitchen to the left. And there's plenty of beer and water and probably some more pizza, so help yourselves. Also, the first fridge has soda and some other drinks. I'm Fred. Nice to meet you. Hi, Fred. Hi, I'm Fred. Nice to meet you.
So what are you doing?
Well, I'm certainly convinced that there's no single tech solution to the solution problem.
That was good, Bill.
Oh, thank you.
Scott.
Scott. Oh, you're speaking next, right?
Yeah.
Oh, I forgot.
Yeah.
Test. Okay.
Cool. Test, test. Hey, all right. Hello. Hello, everybody. Hey, so today we're going to be talking about Cupcakes, Kafka, and .NET Core. Sadly, Cupcakes not included. So first off, I wanted to introduce myself. I'm Jacob Zweifel with TravelScale. With me, I have Sandeep. I've got Srini in the back, and I've got Bill right here, and a couple other colleagues interspersed here and there. Yeah, there they are. So just a brief intro about TravelScale, who we are. We are Toronto-based, but have an office here in Boston that we spun up about a year ago now. We are a global innovation firm that sort of helps enterprises adapt to the new world of doing things. So helping enterprises adapt and thrive in the digital era. We work directly with teams to help transform them into teams that are ready to deliver these cloud-native modern architectures, as well as build those products for other enterprises if necessary. And of course, our socials, I'll provide links to those at the end so you can connect with us. So as I mentioned, part of what we do is we work directly with client teams to help them become cloud native. And that has lended us a lot of Kafka experience. So as we're working with clients to build these cloud native solutions, we've been implementing a lot of Kafka-based solutions in .NET Core using techniques that you're all very familiar with, I'm sure. Event sourcing, modernizing ETLs. We also focus on leveling up our clients and helping them use these cloud native tools. And we have a couple approaches for that. One is we do pair programming directly with them, where we are pairing with their engineers and just really walking through implementing new solutions with the engineering team so they can become familiar with the tools. And we also do these university weeks, which are crash courses on various new technologies, Kafka being one of them. One thing we like to do to have a little fun with our University Week courses is have some sort of case study or something that links it all together. And one that we've been having some fun with recently is Cupcakes. That's why Cupcakes. I'll explain a little bit more on Cupcakes later too. In fact, right here. So we liked Cupcakes because they served as a nice analogy for data. So when we're talking about a cupcake itself just is roughly equivalent to just some data, right? And the thing that we really wanted to focus in on here is the idea of a cupcake factory. A cupcake factory being perhaps some older ETL, extract, transform, load, batch process that's running. It's sort of around the modernizing ETL. We have a nice blog post that Bill, my colleague here, wrote, in which we referred to sort of two patterns. There was the crusty cupcake pattern, right, which is your traditional ETL method. There are these big, bulky processes where the only way to really scale them out is via sharding and basically copying the entire bulky process to an entirely new instance. Whereas the sort of modern way to work is through this castle cupcakery, we're calling it, which is all event-based processing, focusing on microscaling, where every sort of task in the ETL is something that can be scaled. And messaging between these tasks is occurring using Kafka. And then why .NET Core? I'm sure there might have been some head scratches there. I'm sure most of us are familiar, Kafka is well supported in Java. In fact, we just had a very nice presentation on using Kafka streams in Java. Thank you, Bill. But .NET Core is rapidly gaining popularity right now. It's a great language for building microservices. It's based on the immensely powerful .NET framework. It can be now run anywhere on any platform, so you can bring that power of .NET and the expressiveness of C# to Linux, to your microservices running in Docker, etc. And then additionally, there's been a lot of community work in the Confluent community to really open Kafka up to .NET. So there's libarty Kafka, which is a nice, very nice C library that's been written out and made available by Confluent. And Confluent Kafka.net, which provides these really nice bindings against the libarty C library. However, in our experience, and as we've been building up and working with clients and building these solutions and presenting this material, we've discovered that there really isn't all that much material out there on the internet to help new developers who are using .NET to get into Kafka. So we've built this very nice reference application architecture, which we've called the Cupcakery, or e-cupcake factories on containers. Like I said, it serves as this reference application. So it's going to have a whole bunch of different patterns written in .NET integrating against Kafka. Very much inspired by Microsoft's eShop on containers reference architecture, if you've ever seen that. If you haven't, I highly recommend checking it out. Microsoft has gone through the trouble of building out this very large reference application with very nice architecture diagrams and Docker Compose and Kubernetes files for just spinning up a eShop experience across containers, all powered by .NET and a React front end. In our case, we chose a series of tools based on our experiences with the clients we've had so far. So we'll be using .NET Core version 2.2. And in particular, we'll be focusing in on Web API, Signal R, and using the iHosted service or background hosted services. Of course, Confluent Kafka. We'll be using the consumer and producer APIs, Kafka Connect. And this is pretty exciting. We have a chance to use the brand new Confluent Cloud, so the hosted solution that Confluent is offering. And then a few other modern tools as well. So MongoDB, React for the front end, Docker, Kubernetes, and this has all been deployed out to the Google Cloud Platform. And with that, as I just said, it's all been deployed out to GCP. So we'll be able to run a nice public demo here today. We, of course, have backups, but hopefully it will be all public and it will just work seamlessly. Just real quick, I wanted to give you a tour of our architecture here. So as I mentioned, we've got a single page app on the front end. It's going to connect to our backend via two primary methods. There's WebSocket connections that are going to a series of microservices from the front end to the back end using Signal R. And then the single page app will also be posting to some RESTful endpoints as well. And then each of the microservices are communicating with one another through our streaming platform, in this case, which is Kafka. And then when necessary to persist data, we have connectors going out to MongoDB, to older relational DBs, and some other interesting things that are in the architecture as well, but we might not actually get into the demo, such as a PCF log sync, memory cache, a few other cool things are there in that reference architecture. So without further ado, it's demo time. So I'd like to bring Bill up, who will be running through our demo. Bill?
Right. He's awesome. Yeah. Yeah, so we've been working on this for a few weeks. Tribal Scale is invests a lot of time for us to actually level up and give back to the community. So we've developed this open source library to help educate everyone around event streaming and microservices in the way Microsoft's done, but with our own sort of slant. I was up all night last night trying to put the final touches on a Blazor front end, and I failed miserably at 4 a.m. So I'm a little out of it. So so what we're going to do is we're going to show the front end. So we have several use cases, and depending on the time, we'll see how many we get through. But our first use case will be one-on-one. So we'll go back to the Cupcake Factory. So we created an article, and we used the metaphor of a cupcake factory. And if you consider the ETL process, right? ETL process is pretty much the same, right? You're importing data, you're validating, you're fixing, you're enriching, and you're spitting it out somewhere else. We've been solving the same problem for years. Like, I've been doing this almost 30 years. This is always something that I have to do. Import data, clean it, and shove it somewhere. And I still can't believe we're still doing this stuff. You know, it's just weird. You know, we're still doing it. So we created this metaphor around a cupcake factory, right? Think about like if you had this great idea of a cup, you have this great recipe. Think of this, a cook that says, I know how to create this recipe. I'm going to create this special kitchen. I can create cupcakes. I can create 1,000 cupcakes a day. As long as I have a kitchen that I can do mixing, I can do baking, decorating, and boxing. And it's all within my reach, and I can do 1,000 a day. It's going to be great. And that's the most efficient way to get to the market. And if you think about an ETL process and a batch script, where you have a script that's doing that, it's importing, it's validating, it's fixing, and it's all in one script. Think of an SSIS package or any kind of script, a batch script. It's thinking about the process first and not the data. And once you change your thinking to event streaming, you're thinking about the data first, where I have a record, and this record needs to be validated, it needs to be fixed, it needs to be enriched, it needs to be sent off to the world wherever it needs to go. And once you do that, you can gain scalability, you can gain flexibility, you can gain a lot of efficiencies. And so we took. So this demo is just the the good Cupcake Factory. It's not the crappy one, because we don't want to go there. So like the architecture says, we have a Cupcake Factory, right? It takes orders. The orders get transferred to a couple processes. So an order comes in, it goes on to a to be mixed topic. Then we have a process that mixes. The mixer mixes and puts it on the process to be baked. The baker picks up the topic or the data, cooks it. It's a long-running process. And then it puts it on another topic to be decorated. It's a cupcake that needs to be decorated. and now it needs to be boxed, right? So if you think about an ETL process, it has a bunch of stages. It's very similar. So think about Cupcake as it could be a trade data, it could be any data. Don't focus on it being a cupcake. Okay. I'm so hungry. So anyways, Sandeep, can you? Tech support.
Hello. So I'm gonna bring.
So this is an interactive demo, right? So I'm gonna need 4 volunteers. That's gonna help us. So just 4 for now, and then we're gonna open it up to everybody, okay? And I feel really bad because after Bill's talk, this is like the Animal House because this is so low tech and low, like not like Kafka internals. This is just, we're just doing event processing and some of the stuff we've been doing in .NET Core, right? And back to why .NET Core. .NET Core, once we've gotten the ability to compile to Linux, it's opened up the whole new world for us. We're no longer, I mean, we're still the red-headed stepchild of the Apache projects, but we're gaining, and luckily Confluent has given us the ability with Liberty Kafka to actually take advantage of Kafka and use it in our enterprises and be able to embrace Apache.
So what we have here on the terminal is a couple of terminal windows where we are actually watching the messages coming into different topics. So we have around 5 topics. The first one is the order request topics, where when we submit the order, this message would come and sit in this topic. And as it gets processed and move into a different roles, the message moves from one topic to the other. We can see that live. So just for example, here I'm actually, this screen is for the customer to place the order. And here I'm placing the order. Once you place the order, you'll see that the offset gets updated here. Let me bring it down. So if you look at that, it gets updated. Yeah. And there are, so this is the next screen where we are actually representing the mixer role, wherein we have like 9 order requests to be mixed. So as you hit this mix, this will actually move that message from that topic to the next topic. So you'd see that the message coming here increment by more than 5. So let's mix that. So as you mix it, the number of orders are reducing here in this stream. And then they're coming here or to the baker role. And as you process bake the cupcakes, they would come to the decorate stream. You can see that they are updating live. As you process the orders here as a decorator, they'd finally come to the packaging. And there you go. They go off from here to the shipping. So if you look at the topics here, you see that the message flowing through real time between different topics.
For the dashboard?
Okay, yeah. There is also a dashboard here. So to represent, you can look at see that this is the number of orders which are ready to be mixed, number of orders ready to be baked, and so on and so forth. So actually, you can open it up.
So what we've shown here is that we've seen orders go through each through a bunch of topics, and each process gets them and is able to act on and transform them into a different piece of data, and it passes on to another topic. The boxing piece is meant to be more of a Kafka stream, and we haven't implemented it, but it's meant to join the order with the and aggregate the number of quantity of that order and box it. So that's the end-to-end process.
And do you want to actually say open up and then?
Yeah. So that's the end-to-end process. So what we wanted to do, let's go all the way back to the beginning of the demo in the presentation. So the next piece, so that's end-to-end, right? So we have orders coming in, and then Cupcakes they go through a specific process. Now, what do you do when you have to scale? So we mentioned micro scaling. So each process may need to scale, right? The baking process is going to take a long time. It takes 20 minutes to bake a damn cupcake. So what are you going to do after? You want to be able to process things at different rates, right? If you have a batch process, you can only shard. You can only take that process and add another VM and scale that way. But in an event streaming, you can micro scale. So what we wanted to show here is that we have these are open an open URL. So if anybody want to take out their phone and take the role of baker or mixer or whatever, go to the slide, the first slide, and there's I put the URLs there. First in the demo down there, like 7 probably. Yeah. We're not professional presenters, by the way. And this is a free talk, by the way. All right, so if anybody is interested in playing this game, it's wicked fun. Go to Workers, okay? It's 35 237 117 93 port 3000. Pick a roll. You win. You get a pen that's yellow. Talk to me. Awesome. So everyone pick a role, right? And so with SignalR, what we're doing is every connection becomes your own consumer. So Kafka is actually the ability of Kafka, the Kafka built-in mechanisms is allowing us to round robin the load to as many people that connect as they can. So if we have 1,000 cupcakes and we have 100 mixers, everyone's going to get, I don't know, math. There shouldn't have been math here. Sorry, I should not have gone to math. Okay, so everyone's got that. Pick a role and do it, and we're gonna add 1 billion cupcakes to the orders. We're really good. Everyone loves our cupcakes because we're wicked good. Wait, add more. No, add more orders. So no, change the quantity to. Are we splitting them up into singles? Oh. Okay, so where is the go to the dashboard? See, if only I had more time in the night, I would have had a Blazor app that actually showed a lot more, but I suck. Okay, so this is kind of the dashboard, and it's showing us how many records are in each queue. Unfortunately, it's just showing it from the start because we didn't do any math. We're math challenged. We don't do math, but we do adding. We're really good at adding. So who's mixers? How many mixers do we have? We got 3 mixers. How many are in your queue? All right, add more. Sales. Show us the paper. Show us the bag. Is that what Jared used to say? Show us the bag. All right, so
I'm also submitting this one.
you're submitting. So how many we got now? 3. You can submit orders. Sure, go ahead. Oh. 300 orders? That's a great sale. Bang! Rock and roll. Well, so the point is, we're using Kafka to actually do the load balancing for us, because once the consumers, so the idea is our SignalR connection is using the same group ID. So as every time you guys connect, you're creating a new consumer in the same group ID. So you're having competitive consumption of all the topics, all the messages on the topics. But this dashboard is using a different group ID. So that's how we get the total of 339 orders, and everyone else gets a split of whatever's left. So that's our demo of scaling in .NET. And if anybody, I know everyone loves, most people, if you come here as a Kafka person, you're probably all Java people. You have no idea what SignalR is, right? So SignalR is basically a web socket implementation library that Microsoft loves, and they've embedded it into .NET Core. So we're using it, and it's awesome. And yeah, that's all. Yeah. So we covered end to end how we're using producers and consumers in .NET Core. We covered how we scale using SignalR and competitive consumers, or cooperative consumers and competitive consumers. Our other use case, what's the next one? Error handling. So this is where we go into the fictional world, because we kind of ran out of time. But what we were gonna do is what happens when we get really terrible bakers, right? They read too many books and they burn stuff all the time. We can't send that burnt cupcake to anybody, so it becomes an error. In our world, we take that burnt cupcake and we throw it onto an error queue, and that error queue gets redirected back to the mixer and says, you need to remix this because that baker is terrible and it just burns stuff. So the way we've designed, do we have any sort of visual? No? Well, so our error strategy is basically when the baker burns something, the message goes onto the error queue. The error queue is consumed by the mixer and is reintroduced into the cycle and reprocessed. Yes, because we reuse the same, we have a retry count, and once, depending on our policy, then we'll end up sending it to a dead letter queue, and the order would be nullified or would be alerted. So I think, did I mention that? So we're kind of giving this back to the community. This is an open GitHub project, and we're going to keep working on it, and just basically taking these patterns that we've implemented in practice over the past year and a half. Jacob's actually been working on Kafka for like 1 billion years. Before it was even created, Jacob was working on it, but literally he's worked on some of the biggest customers, but we've only been doing it for about a year. You, sir? Well, the decorator, yes, exactly. Yeah. But that's the power of event-driven microservices, is that once you've opened up the batch process, now you can introduce all this variability, and it's hard to explain it to a lot of people that are just SSIS, Informatica, that I need a process to process my data, rather than I have data that needs to be set free, man. I don't know. I'm just kidding. But seriously, when we think about data first, it opens up possibilities, and that whatever that was. Timeline. We're doing it all the time. I will have Blazor this weekend, man. I was so mad that I was so close. I was like, 10 minutes. I need one more 10 minutes. And then it's 5 o'clock and I had to join the stand-up, so. You want to keep going? Is that? So we covered end-to-end, we covered scalability, we covered our error sort of burnt cupcakes scenario. Our other sort of use cases, how's we doing with time? Well, I know everyone wants to drink more beer. Well, I do. So our other scenarios were legacy systems, integration with legacy systems. What if you already have an order system that generates orders and this new fancy cupcake thing? So we were going to use, well, we've already implemented a SQL Server CDC that would dump an order table from SQL Server into our order queue that would represent more orders, and then we could process those on a one-way replication sort of scenario. So that's our legacy scenario. Yeah, you want to keep going? And then external systems. What happens at the end? So in our sort of make-believe world, our Mr. Rogers universe, once the cupcake's decorated and put into a box, where does it go? Well, we would use Kafka Connect modules that would live on the Kafka server that would end up going to Mongo, which is in our architecture. Mongo being a new, modern, cool thing to use. Yeah. So, do you wanna cover the gotchas? What's that? Oh yeah, double click on it. So again, Jay-Z is our most experienced Kafka guy, probably in this room besides you. And Bill.
Just hit the
top right
present
side.
button. Yeah, so thanks Bill and Sandeep for that great presentation. By the way, Srini never came up, but he built a lot of this as well. So big round of applause for those three. We just real quick at the end here wanted to share some gotchas that we ran into while using .NET Core and Kafka together. One of them, and this is a pretty big one, especially after following Bill's presentation, is there isn't a Kafka Streams equivalent in .NET Core currently. Since the libraries in .NET Core are still pretty new, of course, the team focused on implementing the lowest level abstraction first, the consumer and producer APIs. So if you're looking to use that next higher level abstraction, the Kafka Streams, you do have to look at other options. Either you need to step even higher level than the Kafka Stream and turn to something like KSQL or some other data streaming semantics, or one option that we've considered but haven't quite gotten into yet is the idea of perhaps using a Java application that we're loading in as a sidecar and communicating over RPC or something to our .NET application. That'd be one avenue we could explore and put into our reference architecture. We had a lot of pain around deployment to private clouds at first, especially to PCF and especially with Kerberos. So we found that the Linux containers used in PCF by default can have the libraries necessary to perform the authentication over the Kerberos protocol using a key tab. So we had to do a few hacks there to first download the binaries, copy them into our output container, and then ship that container over to PCF. Luckily, that's fixed now though. So as your PCF deployments, if you're using PCF, start introducing the new CF Linux FS3 stack. We've actually committed back to Cloud Foundry the necessary libraries to be included into the core image. So I haven't gotten a handwritten letter yet, but so going forward, hopefully you will have less problems if this is your particular use case. Also, when we started using the libraries, they were still pre-release, so there was a little bit of pain when you're going from the earlier beta revisions of the Confluent Kafka library to the version 1. But now that version 1's out, I suspect that will be a lot less painful going forward. We also have, of course, run into pain managing offsets, but I think everybody, when they first start using Kafka, runs into trouble managing offsets. So that's not specific to .NET Core, but just a gotcha to keep in mind, as especially when you're brand new to Kafka, just managing offsets and making sure that you're doing the right thing, especially when it comes to a topic versus a partition. Really be careful there. Also, we had some pain points with debugging on Windows, which is also a little bit related to the Kerberos issue mentioned earlier as well. So as we were trying to debug our applications against a hosted Kafka implementation that was secured with Kerberos, we had some problems using Visual Studio Code to attach to a debugger that was running in WSL, just all sorts of pain in there. So watch out for that. And related to that as well, make sure that your developers have adequate resources on their machines. It's, of course, very nice to have a local Kafka cluster running whenever you're doing development. It just makes things a lot easier. But the best option for that, in our experience, is to host the cluster inside of Docker on Windows. Docker is still pretty new to Windows, especially Windows 10, and there's a little bit of pain there. Microsoft is actively making it better, but right now it can be pretty painful. It kind of crunches resources. It's a little slow. File system access isn't all that great right now, but it's getting better. It's getting much better. I'll get a hold of somebody over there. And yeah, that's really it for our gotchas. We do want to just give a quick shout out to 2 community members, or I suppose Confluent employees at this point, yeah. Magnus Edenhill and Matt Howlett. Magnus Edenhill seems to be the primary contributor to librd Kafka, and Matt Howlett being the primary contributor to confluentkafka.net. Without their hard work, none of this probably would have been possible without a whole lot more work on our part.
It's a really badass picture of Magnus.
Yeah, check out that sledgehammer.
Exactly right.
And that's all we've got. So definitely check out our GitHub repo. We have provided the link to the demo UI right there, and this very nice QR code will take you straight to our GitHub repo. Along with, we have a list of links to our various social profiles if you want to track us down, as well as a few blog articles that we've written that sort of provides more detail about some of the things we've talked about here today.
And we're not hiring, but we're looking for work. So if anybody wants to talk to Brian over there,
that's your guy. So if I could have Bill, you 3 come back up. Any questions?
and Srini has spent hours and hours and hours writing all this code, and I didn't help him at all.
You tried.
I kept saying, oh, I'm going to totally help you with that commit, and I never did.
That's okay. Sorry.
Cool. Any questions?
Just one comment. Less than 4 o'clock in the morning, you can take your current cupcakes, put it back in the batter for 2-1. You're just going to keep destroying batches.
Well, there's a thing called twice baked cupcakes, and you never know if that's going to be good or bad. Well, you've heard of twice baked spuds, right? Twice baked cupcakes are twice as good. Well, the idea would be you'd have a policy on retries and then you'd go to a dead letter queue.
All right. Thank you, everybody.
Thank you very much. Just wanted to thank everyone here, especially Confluent and Shay for putting this together and organizing it. Just real quick, just curious if people had any suggestions or ideas for things they'd like to see at the next meetup. We're going to be working with Confluent to get another one on the calendar and scheduled. I know that they're always looking for people who either want to do demos or presentations. Is there anything offhand that people would like to see?
Just low-level implementations of what Kafka Streams does without Kafka.
Low-level implementations of Kafka Streams. So anyone who would like to present that, definitely reach out. All right. Thank you very much, everyone. Have a good night.